If you read the headlines lately, you'd probably think the debate over the future of driving is totally settled, right? The whole narrative is basically that battery electric vehicles are the one and only inevitable path forward. But does the future really belong solely to the battery car? What actually happens when we strip away all the hype and just look at the naked physics, the engineering realities, and the hard, real-world energy data? Well, welcome to today's Explainer. We're taking a deep dive into some truly fascinating automotive research that completely challenges those mainstream assumptions. So buckle up, because the race for the mobility of tomorrow, it's really just getting started. The core thesis of the research we're breaking down today opens up this totally new and, honestly, incredibly exciting perspective. The main idea is simply this: there is no single magic silver bullet for how we get around. Instead, the physics, the engineering, and the data all point us toward what the source calls a highly modular menu of different propulsion systems and some really intelligent combinations. So here's our roadmap for today's Explainer. We'll start with the pure physics of propulsion, then look at energy and its storage, dive into the technology of energy converters, compare the chemistry from cold to extreme, and finally, serve up that modular propulsion menu. All right, let's kick things off with Section 1, the pure physics of propulsion, the absolute basics. The author of our source text frames this so wonderfully. Ultimately, all roads lead to the wheel. I mean, whether your journey has you navigating the dense, crazy streets of Paris, or you're just cruising across the vast stretches toward Moscow, at the end of the day, the drive wheel really only needs one thing to move you forward: force applied over a lever arm. Just a simple, basic rotational torque. That is the fundamental physics requirement of mobility, period. And to actually generate this required torque, well, practically speaking, there are really only two types of machines available to us in the real world. On one side, we have electric motors, which use magnetic fields to create rotation, and on the flip side, we have heat engines, which convert pressure into motion. And that's it. That is our absolute impartial baseline for creating movement. Moving right along to Section 2, energy and its storage. This is where that force actually comes from. So there's obviously a massive global discussion right now about banning combustion engines to hit climate neutrality. But our source material introduces a really sober, factual argument here. If we truly want climate neutrality, we should really be talking about banning fossil fuels like coal and oil, not necessarily the machines themselves. Why? Because the harsh reality is that an electric motor is only as clean as the energy source that charged its battery. Look at these numbers for our current global electricity mix. Coal and peat make up over 38%. Gas is sitting at 23%. Hydro and nuclear combined offer 26%. And wind energy, which, gets an enormous amount of praise, currently makes up just a tiny 4.4% globally. This data brilliantly and maybe a bit brutally illustrates that on a global scale, electricity is unfortunately far from entirely green yet. Now, you might be sitting there thinking, okay, sure, but what about hydrogen? Isn't that the ultimate clean savior? Well, let's look at the data impartially. 2%. According to the source data, right now, only an incredibly small 2% of global hydrogen is produced via clean electrolysis using green electricity. The massive remaining 98%? It's mostly derived from burning natural gas and oil, which produces the exact CO2 emissions we're trying to eliminate. And then we hit a massive physical hurdle when we try to bring stored energy on board a car: energy density. To put this into a relatable perspective, a typical lithium-ion battery stores about 0.1 kilowatt-hours per kilogram. Liquid fuels, on the other hand, they deliver a massive 12 kilowatt-hours per kilogram. Guys, that is a more than 100-fold difference. So the crucial takeaway here is this: if you need 20 kilowatts of power for one single hour of driving, you have to lug around 200 kilograms of batteries to get it. But the liquid fuel required for that exact same power output, it weighs practically nothing in comparison. Which brings us to Section 3, technology of energy converters. Welcome to the engine room kitchen. Let's start with the fuel cell, mostly because it's so often misunderstood. Just to be totally clear, a fuel cell is not a motor. It doesn't actually turn any wheels. It's simply an energy converter. Its sole job is to produce electricity on board for the electric motor. The source uses this brilliant analogy to make it graspable. Think of a Big Mac. Imagine the buns are the gaps where gases flow. Hydrogen on the left, oxygen on the right. The meat patty right in the middle is the electrolyte, a polymer membrane. And here is the clever trick. The hydrogen protons are pulled straight through the meat toward the oxygen. But the electrons? No way, they can't pass through. They are forced to flow all the way around the outside through a cable. And it's exactly this flow of electrons that powers your car's motor. At the end of the process, it all just combines harmlessly into water vapor. But here is the really fascinating twist. We don't actually have to rely on complex fuel cells to generate electricity on board. A classic heat engine, a standard combustion engine, can actually do the exact same job as a generator. Think about it. If a combusting engine doesn't have to directly drive the wheels, it completely avoids that super inefficient, constant revving up and down you get in stop-and-go city traffic. Instead, it just runs constantly at its absolute sweet spot RPM, and an engine running permanently in its perfect optimal range can be tuned to be so incredibly efficient and low in emissions that it suddenly becomes a very serious competitor to the fuel cell. Next up, Section 4, Chemistry, going from cold to extreme. What is truly mind-blowing here are the gigantic differences in reaction temperatures and how these materials actually make contact. Just look at these staggering differences in their environments. In batteries, materials react in a resting state, separated by mediums at a pretty comfortable 20 to 80 degrees Celsius. In fuel cells, they're actively flowing past a membrane. But in a heat engine, we are talking about the direct contact of materials at a brutal 2,000 degrees Celsius. To explain why this extreme environment actually matters, our source offers another fantastic everyday analogy: making mayonnaise. Think about when you whisk mayonnaise in a bowl. By vigorously stirring it, you're creating massive turbulence, which generates a huge contact surface area between the egg and the oil. Well, in a very similar way, inside a combustion chamber, air and fuel are mixed with extreme turbulence, directly, with absolutely no separating walls. Combine that massive contact area with 2,000 degrees of heat, and the particles have so much kinetic energy they practically burst out of their chemical bonds. This makes the release of energy unimaginably faster and more efficient than in a resting, relatively cold battery. All right, let's bring it all together in Section 5, the modular propulsion menu, the mobility menu itself. So we finally arrive at the very first item on our modular menu, the pure EV. The data shows that around 80% of European city dwellers drive less than 50 kilometers a day. For this specific use case, a small, lightweight 20 kilowatt-hour battery is absolutely perfect. I mean, if you can charge it at home overnight, you're driving 100% emission-free locally. And crucially, you aren't dragging around tons of useless, expensive, dead battery weight every single day just to account for some theoretical maximum range you hardly ever use. Next up on the menu is Concept 2, the range extender, or serial hybrid. This is exactly what we discussed earlier with that optimal generator idea. A highly compact combustion engine acts purely as a generator, supplying constant electricity to a smaller battery and the electric motor. It operates beautifully at its optimal RPM, completely kills range anxiety, and it can actually be run on climate-neutral fuels like hydrogen or biogas. Plus, it's often significantly cheaper to manufacture than a highly sensitive fuel cell. It's a huge win-win. And hey, if you're sitting there thinking onboard generator sounds, well, kind of boring, check out these numbers. Jaguar actually built a concept vehicle that uses 2 ultra-compact gas turbines to generate electricity for 4 electric motors. The result? 0 to 100 kilometers per hour in an insane 3.4 seconds, with a top speed of 330 kilometers per hour. And the fuel consumption? The equivalent of just 4 liters per 100 kilometers. This data just proves the absolutely staggering potential hiding in this engineering concept. Building on that excitement, let's look at Concept 3, the parallel hybrid, which you probably know as a plug-in hybrid. This is the ultimate adaptable duo. It perfectly combines the physical strengths of both machines. You get the instant torque of the electric motor right from a standstill, which is absolutely perfect for stop-and-go city traffic and zipping away from green lights. But then, when you hit the highway, the combustion engine seamlessly takes over, utilizing its immense efficiency at higher speeds. It's a system that flexibly adapts to exactly what you need, exactly when you need it. Finally, Concept 4 proves that different technologies don't actually have to compete. They can completely complement each other. Just imagine this: a combustion engine driving the wheels, but it's paired with a small fuel cell for the vehicle's electrical system. Both of them draw from the exact same tank of clean fuel, like bioalcohol. The fuel cell silently generates 5 to 10 kilowatts just to run the electronics, the pumps, and the valves. Taking all that mechanical load off the main combustion engine causes its fuel consumption to drop drastically, skyrocketing the vehicle's overall efficiency. How cool is that? All of this incredible engineering leads us to the ultimate conclusion of our source material, perfectly summarized in what the author calls Thesis 46. The mobility of the future is not a rigid, monolithic block. There simply isn't just one single winner that takes all. Instead, the propulsion systems of tomorrow will be a highly modular menu, one that is flexible, highly intelligent, and perfectly adapted to existing infrastructure and how people actually drive in the real world. We've seen today how incredibly creative engineers can be when they really leverage the laws of physics. Everything from small, smart city EVs to staggering turbine sports cars. Because we have this entire adaptable menu of solutions ahead of us, I want to leave you with this final thought. When you look at your own daily routine, your own driving habits, which specific combination of energy, storage, and propulsion type on this modular menu actually fits best with your personal lifestyle? The next time you get behind the wheel, give it some thought. Thanks so much for joining me on this deep dive into the engineering of tomorrow. See you next time on The Explainer.